Welcome to the Health AI Brief, breaking down the AI shaping our world one concept at a time. Last time we took a bird's eye view of reinforcement learning, the idea of an AI learning through trial and error. Today we're getting into details of a challenge that sits right at its heart. It's a problem we clinicians also face constantly. Think about managing a patient with a complex treatment-resistant condition. The guidelines give us a reliable, well-trodden path. That's our safe bet. But we also know that there's a novel, off-label combination that might yield a better result, though it's less certain. Do we stick with the proven standard, or do we risk trying something new for a potentially greater reward by developing a new clinical trial or something like that? That right there is the core question of the exploration-exploitation dilemma. This is one of the most foundational concepts in reinforcement learning. The AI agent has to constantly decide between exploiting its current knowledge, using the strategy it already knows works currently best, and exploring to see if it can find an even better one. An AI that only exploits will get stuck in a rut, never improving beyond its first good discovery. An AI that only explores will act randomly and never capitalize on what it's already learned. So how does it balance this? One of the classic exploration strategies is called epsilon greedy. Essentially, the AI follows its best known strategy almost all of the time, say 95% of the time. But for that other 5%, that's the epsilon. It deliberately takes a random action just to see what happens. It's a bit like a consultant who, despite having a preferred antibiotic, occasionally asks a colleague to look up the second line option, purely to ensure that they both stay current and don't miss a potentially better choice. This dilemma gets much harder in environments with so-called sparse rewards. Imagine trying to find the optimal management for a chronic condition where your feedback, a change in a key biomarker, only comes every 6 months. If an AI explores randomly, it might never see a positive outcome, so it has no signal to guide its learning. It's like wandering in a desert with no landmarks. An AI designed, say, for drug discovery might be programmed to explore aggressively, accepting more risk for a higher chance of a breakthrough. In contrast, an AI guiding real-time patient management in the intensive care must be designed to exploit proven strategies, with only very careful, limited exploration. The approach taken determines a lot about its potential for both groundbreaking insights and unexpected error. So that's the exploration-exploitation dilemma in a nutshell. Next time we're going to discuss one of the most elegant ways developers can manage this problem by creating a structured learning path for the AI, much like in medical school.